Okay, hello everybody. Welcome to this interview with Dr. Edward Johns as part of the Roundtable interview series, where we'll be discussing real-world robotics. Dr. Edward Johns is the director of the Robot Learning Lab at Imperial College, where he is also a senior lecturer, associate professor, and Royal Academy of Engineering Research Fellow. His work lies at the intersection of robotics, computer vision, and machine learning. He received a BA and MEng in Electrical and Information Engineering from the University of Cambridge and a PhD in Computer Vision from Imperial College. After a postdoc at UCL, he returned to Imperial College as a founding member of the Dyson Robotics Lab with Andrew Davison, where he led the robot manipulation research. In 2017, he was awarded a Royal Academy of Engineering Research Fellowship, and in 2018, he was appointed as a lecturer and founded the Robot Learning Lab. It's our pleasure to have you with us today, where me, Daniel Lenton, and Ronald Clark, Dr. Ronald Clark, also from Imperial College, will be discussing some interesting topics around real-world robotics with you today. So I'll dive straight in to the first question then. So just to kick things off then, I'll start with quite an open-ended question. Do you think it will eventually be possible for fully dexterous robotic AI to emerge from an algorithm as simple as reinforcement learning?
So I think that when we look at reinforcement learning applied to real world robotics, there are a lot of factors that often people overlook when they train simulation only agents, which is where a lot of the foundations of deep reinforcement learning are coming from these days. So a couple of these are fundamental differences. One being that reward functions don't kind of magically appear for free, and actually we have to tell the robots what those reward functions are in the real world. That there's not a sort of underlying mathematical formulation for a reward function that the robot just happens to know about. And so if we did want to train a robot to be able to perform any task in the world, then somehow we would have to define all the reward functions for all of the tasks. And often that's done with providing a demonstration of the task. And then that essentially becomes imitation learning rather than reinforcement learning, or at least a combination of the two. So defining the task using imitation learning, and then perhaps solving the task using reinforcement learning. So so one thing is that it's actually not so simple as saying let's just use reinforcement learning for everything, because there's got to be some kind of way of defining those tasks in the real world. But also I think that it might be possible for a human to go away and define reward functions for every conceivable task, and scaling that up using data collection from lots of humans with lots of demonstrations might be possible. But then chaining together those skills, so how a robot would decide on which skill or task to perform next, that's something that reinforcement learning isn't really going to solve, because you would then essentially have to have an extremely pure reward function, like I don't know, survive, or always do what the human says, or something, which is too pure, I think, for a robot to learn through something like reinforcement learning, because that's essentially how evolution happened. And I don't think we're going to be able to replicate evolution in the real world with robots, or even with simulations.
Do you think then that's a fundamental constraint? Because that's actually just what I was going to quickly say, and then I'll pass over to Ronnie as well. But what I was going to say is, maybe right now, obviously, when we have very specified subgoals and everything, then that makes a lot of sense. But just hypothetically, when we talk in the abstract of where the future could take us in centuries, given that evolution has demonstrated that a simple evolutionary algorithm seemingly has generated very sophisticated intelligence, do you think that's something that's within the realm of possible, even if it's a little bit far-fetched today?
I think, like, philosophically it's possible, but I don't think technologically it is, because it would result in too much failure, and it would just be so expensive to have so much failure in terms of both the hardware, different hardware setups evolving, if we're talking about just applying evolutionary algorithms to physical robots, then I think the issue is what do we define that pure reward function to be? Because we can't do survival anymore. That's, a robot is going to survive just by keeping it plugged in. Also, it then raises these kind of sci-fi questions of, well, if a robot's only goal is to survive, then what on earth is that going to lead to? So defining that pure reward function of an evolutionary algorithm is very, very difficult. And often people use evolutionary algorithms to enable a robot to solve specific tasks by exploring the world in a very, very diverse manner. But that's still constraining the robot to just learning specific tasks, which then will need to be defined by humans. So yeah, I don't really imagine that we will solve this through at least the first generation of kind of AI that appears to be human level, coming from pure evolutionary approaches.
Sure. Do you have any thoughts to weigh in on this, Ronnie, you think?
Yes, I think there's 2 points that I kind of want to discuss related to that, because the first is the nature of the simulated environments in which the reinforcement learning or imitation learning is usually done. So the current reinforcement learning approaches, you kind of have to train in simulated environments, because there isn't a way to have that amount of exploration or sort of run the number of trials needed to actually do it in the real world. So I was just wondering, Ed, do you think there is a limitation, kind of a severe limitation introduced by using these simulated environments? Because obviously the physics or the accuracy of the simulations aren't anywhere, near what the real world actually does. So there's kind of all these quirks or anomalies that are introduced in the simulations that don't exist in the real world. And there's lots of stuff in the real world that isn't really modeled in the simulations. And so I was just wondering, what are your thoughts on that? Do you think simulations are the way we should be training these agents, or do we need to go to the real world?
Yeah, I think simulation-based robot learning is problematic, and I don't think this is how we should really be training robots. I think it's fine to be developing core algorithms, but I think we shouldn't imagine that robots are going to emerge with human level AI or dexterous capabilities just through simulations. And there's a couple of levels at which simulations differ to the real world. So the first level is simply not being able to model real world dynamics. So some people will say, oh, okay, well, we'll just train robots in simulation and then we'll just deploy them in the real world. And that does work for some specific cases where we can kind of overfit the simulation parameters to a specific task, and we can do quite a lot of engineering. So something like locomotion for quadrupeds has emerged as being something where we can actually do quite good sim to real transfer. But that's a very well-defined task with quite a pure reward function, which just says, well, keep moving forwards as much as you can. Whereas for manipulation, there's billions of different tasks out there. So you couldn't really overfit your parameters to all of these different tasks. And then the other level where there's difference between simulation and reality is just the setup of how training actually works. So in simulation, you have this reward function for free, and also you have automatic environment resetting. In the real world, you don't have either of those. The reward function has to come from a human defining the reward function, let's say, for a new task, and the human would have to reset the environment every time the robot fails. So when you have that kind of difference between simulation and reality, the actual algorithms themselves are developed within a different paradigm as to how they would actually be trained in the real world. And therefore, reinforcement learning researchers are optimizing those algorithms towards different setups than they would actually be deployed in the real world. And as such, the researchers probably aren't optimizing them in the right way, under the setup that they would actually be deployed in the real world. So one example of that is a lot of reinforcement learning algorithms optimized purely for data efficiency. So you have these graphs of where the y-axis is success rate and the x-axis is the amount of data. And that's quite a pure machine learning metric, and it makes a lot of sense in the machine learning community. But when you take that into the real world, what we really care about is time efficiency, or maybe the amount of time that a human spends teaching a robot. And that has to then factor in things like the setup of the reinforcement learning algorithm in the real world. You know, what extra apparatus do you need? How much time the human would spend providing demonstrations or resetting the scene. And when you start to factor in all of these, then actually the pure kind of reinforcement learning approach doesn't look so appealing anymore, because there are a lot of human has to do there, which are a burden on us beyond simply the amount of time or the amount of data that the robot will be collecting.
Yeah, I think that makes a lot of sense.
So like roughly, how efficient would you say current reinforcement learning algorithms are compared to kind of actual biological learning? Like in terms of the number of episodes or the number of kind of trials that these agents need to do before they can actually learn a skill?
Well, I think if you're talking about biological learning in terms of evolution, then probably much quicker. To get to human level capabilities, it took billions of years, whereas robots can learn much quicker than that. But if you're talking about in terms of comparing to how quickly humans learn, then certainly much slower. And really, the only things that humans use reinforcement learning for are kind of skills where you have to become an expert relative to other humans. So playing sports, for example, or playing musical instruments where there's some kind of muscle memory or precise kind of dexterous manipulation required. Whereas most of the stuff we do day to day, we don't learn through reinforcement learning. We just learn through exploring the world as a child and learning models and being able to deploy those models in new situations. We don't often get told a task and then sit there and learn it through trial and error over and over again. So I think there's this misconception in the reinforcement learning community that reinforcement learning is the way that humans learn. Often that's written as the motivation for reinforcement learning, but when you think about it, it's not really how humans learn until we get to the point where the task is too complex for us to use our previous models of the world, and we have to start doing trial and error. So we have to start swinging a racket to try and hit a ball, because that's not something we ever learned as a baby, or learning how to play a guitar, because that's something that's new and something that the average human just hasn't picked up on through their life. But yeah, I think this idea that humans learn everything through a reward function, which they then optimize for, isn't true, because babies don't know what they're supposed to be learning in the first place.
Yeah, that was actually the second question I had, because like kind of how does this, does evolution or individuals or biological creatures created from evolution actually have a reward? Because it seems as if it's more like a sort of like, the goal is to survive, obviously, because of if a individual survives, then they obviously just replicate and then carry on the species. But like, there doesn't seem to be an inherent sort of reward associated with their day-to-day kind of activities. Obviously, like if a lion or something captures some prey and they eat it, they get some reward in terms of like dopamine or like not feeling hungry or something. But there doesn't seem to be like a single reward just like governing all these actions. So I was wondering, like, is there kind of a analogous kind of thing with kind of machine learning or robotic learning that tries to kind of mimic that?
So I think, yeah, so maybe what you're getting at is, I guess if we go back to the question of how babies learn, babies certainly explore the world, but it's in quite an unsupervised way. So, you just leave a baby to its own accord. It will start trying to pick up objects and messing around with them, even though you haven't told the baby, oh, can you pick up this object and put it on top of that object? The baby will still do that. So there must be some reason the baby does that rather than just random movement. Okay, there's something which is the baby is thinking, it's interesting to try and explore what happens when I pick this object up. So I think there must be some kind of reward function there that is tailored towards encouraging exploration and encouraging skill learning. But it would be quite a high level reward function that, for example, will encourage a baby to try things that it doesn't know how to do yet, or try things that it's unsure of the consequences of. And that's something we certainly do in robot learning. There are a lot of sort of unsupervised robot learning algorithms which attempt to use predictive models of the future, for example, to encourage robots to states the robot is uncertain of. And that might then lead to robot learning repertoire of skills, which it can then use later on downstream tasks to quickly learn those tasks rather than having to learn them from scratch.
That makes a lot of sense. Okay, so maybe then that kind of leads quite nicely on to the next question, which actually does kind of follow on to some extent, I would say, from that. So I'm just kind of curious. So yeah, taking a step back a little bit, assuming that, you know, artificial general intelligence is the end goal, with embodiment as well, let's say, do you think that both kind of, let's say, fully end-to-end research and also research which combines learning with things we already do know about, such as motion planning, physics, and geometry, do you think kind of both of these tracks are necessary? And what unique purposes do you think these two styles of research serve in the journey towards AGI? And just to give some examples, I would say, for example, I mean, the perceiver IO, a new transformer architecture, is one example of something that's kind of actually taking away some of the inductive bias and from the graph. For example, they solve optimal flow with really very little assumptions of the problem at hand, whereas alternatives such as PwCnet like has a cost volume embedded in the forward pass. That's kind of one example of taking away things that we do know and kind of letting the data speak for itself. Do you think like that track of research, and that includes then end-to-end RL, do you think they have a part to play? Maybe if that kind of shows its real benefit in 50 years or 100 years, maybe when data resources would explode, maybe actually we can kind of keep taking back our prior knowledge from the solution. So what do you think those two tracks of research have to offer, and do they complement each other in some way?
Well, I certainly think both are important. And I think when you're working in AI and robotics, you have to decide at what point in the future are you optimizing your research towards. And some people will say, well, I want to do research such that it goes into commercial products in the next 5 years. And some people will say, I'm aiming for human level AGI, even if that's 50 years or 100 years or even further away.
Yeah.
And so I think in the former case, then you probably would use a lot more modeling and engineering and using methods that we know work now. In the latter case, you would probably be trying to remove some of that engineering and allow robots to learn that behavior. Because if you have the more kind of inductive biases or the more modularization you have, then the harder it is to overcome those asymptotically. Whereas if you can use learning that will automatically optimize for the tasks that you really care about, then hopefully with more and more data, which should be possible in the long term, you would overcome those biases. So I think both are important for impact in society. But in terms of, really achieving AGI, it's really difficult to know. It goes back to the question we were talking about before, but it's really difficult to know what that thing is that the end-to-end system should be optimizing for. And what do we really mean by end-to-end? Do we mean end-to-end control, where observations are directly mapped to actions? I think that's perfectly reasonable, and we understand what that means, but it might fit in with a broader pipeline that, for example, would choose which controller to execute at any one time?
Yeah.
Or do we mean actually learning from a pure reward signal like survival? And in that case, again, we'd have to be sort of somehow replicating evolution. I don't know whether we would really ever have the amount of data or compute to do that.
Yeah, I guess when I use it, I guess more just kind of actually what I should instead say is just kind of the removal of inductive biases of any form, really. Because I guess you can, of course, have an end-to-end trained system which does map from observations to actions, but your computation graph is heavily designed and the gradients you're passing go through something that's been carefully constructed. So that would still, although it's trained end-to-end, like not be necessarily what I mean when I say end-to-end. I kind of just mean removing inductive biases, whether that be through the loss function, through the computation graph, or from any modularization of your system at all. But that includes then the reward function as well, I guess. So yeah, I guess the complete end of that spectrum would be something that is a completely structureless network optimizing something as simple as an evolutionary algorithm. That's kind of the extreme on all fronts of an end-to-end approach. Yeah, so kind of exactly what you're saying, I would say.
Yeah, it's very difficult to say what a system would be without any inductive biases, because you can start off saying that, okay, a convolutional neural network has inductive biases with the convolution, so let's change that to a fully connected network. And then you could say, well, okay, yes, but there's, we've got activation functions in there that we optimize for, and we've got, there's maths in that neural network that we've specifically designed to work. So if you then remove that, I don't really know what you would. I guess you would end up with just data points, and I don't know. I don't really know what that would look like if you removed all inductive biases. It's I guess nearest neighbor in the original feature space might be the closest thing, but then you'd have to do some optimization over those nearest neighbors or something. I'm not quite sure how that would look.
Yeah. I guess it wouldn't be about kind of removing all inductive bias, I guess, but just kind of domain specific inductive biases. For example, like a convolution is like vision specific inductive bias. And I guess also I'm kind of talking about what transformers are doing and stuff, where actually one network can kind of fit all, and there is inductive bias there, and the kind of processing that happens, it's obviously very parallelized and very non-linear, and these are things that we expect the function to be, but it kind of is, I guess, removing the ties to any one domain or task as much as possible. But I guess, it's just kind of, I think, you've already answered the question in so much as, both these tracks of research, I think as well are very important and serve different purposes, whereby the one that really says, let's assume nothing and let's just see what we can do with bigger compute and bigger data sets and take all of it away, that is very scalable if the future does indeed lend us hugely more parallel compute than we have today. Then these are very great methods to really scale with that increase. But as you say, if you want to kind of get robots in the home in 10 years time, maybe your best bet isn't to kind of go down that track. I wonder if Ronnie want to weigh in a bit. Oh, you're on mute, Ronnie.
Yeah. So I think another way to view it as well is kind of for humans, you can show someone an equation or show someone an algorithm and they will be able to use it. They don't have to discover it from scratch by learning or exploring. So I think another way to see these inductive biases is kind of a way to actually kind of show these models how to do specific things without them having to discover it. It's not exactly the same, I think, as the current biological kind of setup, because we kind of embed these relations into the models at the moment. But maybe in the future there could be a way, sort of, a way to actually show neural networks an equation, and they could kind of incorporate that into their computation or something. I guess it kind of goes to meta learning or those kind of things. But I just think you can fit these handcrafted kind of knowledge and inductive biases into neural networks without having to say like, oh, you have to go end to end, or you have to go handcrafted. Like, I think there is a synergy there that people kind of miss.
But do you not then, my question will be, do you not always, like, even if it's on a small scale, do you not always slightly constrain the network by adding this inductive bias? Because, for example, convolutions are incredibly useful and like revolutionized vision. I mean, that was kind of what enabled the kind of next wave of deep learning and everything with AlexNet and so on. But and then with transformers now, actually, you can beat that performance or at least get very close and actually, overcome it without any of that. So even though they're very, very good, maybe, I mean, the trend seems to be, at least so far, that when you have enough data and compute, actually anything we can design, normally there's something that's a bit more optimal and can actually kind of find connections in a more optimal way than we can hand design. So do you think this situation, do you think it's fundamental that adding inductive biases comes with it at least a small amount of constraint on the kind of way that it can learn an optimal function?
So I think it doesn't necessarily have to add a constraint, because for example, you could have parallel channels where you add in a handcrafted kind of computation, and then you have another channel working alongside that doing like a learned computation, and then they fused afterwards. So in the case of like the cost volume or some modules in computer vision, those don't have to be done as a single kind of like bottleneck in the network. You can do them in parallel, but the best way obviously to integrate those with the general network structure is not really that obvious. But I think that the key thing kind of, or the way I always just see it is if you're telling someone or if you're showing someone an equation, or you're showing them some relation, for example, like how to solve like some x squared plus y squared equals 3, or like Pythagoras' theorem or something like that, they don't discover that on their own. They just see that relation or that equation, and then they use it in their work. So I just think there's kind of a way to kind of fuse this handcraft knowledge and the neural networks.
I guess with this sort of this analogy with like human learning across generations, these equations that you're talking about are often just true, and it's not like, it's very rare that scientists in the past have come up with equations that just simply are proved them to be false, right? They're either pure mathematics where a proof is made and it's suddenly that is just true, and it's because it's been proved, or it's more kind of empirical, like Newton's laws, and it's just fundamental, and that's just how the world is. And so it's very, very rare that these equations are later proved to be false. So it's quite difficult, I guess, to come up with the equivalent with AI, where we actually know that this equation that we are giving the robot is pure, and there isn't a better version of that. And so usually these inductive biases are probably not optimal, and they're somewhat, they're better than not having these biases in there because they speed up learning, but they may not be optimal. So I guess the equivalent would be like a field of science where actually, we use previous scientists' knowledge to update our understanding of that field over time, which I'm sure, that happens in computer science, I guess, but more on a kind of conceptual level. So maybe we could give robots approximations of what we think are good inductive biases, and then the robots and the AI can adapt those over time and actually perfect them towards the purer goal that they're trying to achieve.
I think that sounds very interesting, actually. One thing I would just add to that, actually, because it made me think, is that I guess, as you're saying, like in learning, we very rarely have these kind of perfect inductive biases that can just be easily added in. And I guess even when we do, for example, because we have physics, like the laws of physics need to be adhered to, and maybe we should embed that into the model. But actually, if what we want is an efficient control system that can take observations and select their actions. I mean, Sergey Levin gives this very clear example where when you're catching a ball or something, you could actually like try to model the 3D position of the ball, model its acceleration and so on, and like, you know, plan yourself to be there at the right time. But actually, for example, you then, what you might then do is just keep it in your horizon at the right height. So you, as you're kind of running to catch it, you just keep it in your eye line at a certain angle, and then you arrive, you know, at the right place at the right time to catch the ball. And so I guess, yeah, there's lots of cases where you could solve many problems, including control problems, by modeling everything perfectly. But to actually get a very responsive closed loop controller that's like optimal in terms of response time, for example, you might not need to kind of model these things. So I guess that is, as you're saying, kind of, it's not clear what inductive biases we even want. Even if we have them, it's not clear that they're optimal with what we actually care about in the computation graph.
Yeah, I think, yeah, I certainly think inductive biases in terms of physics, this. I mean, I don't think humans actually have very good physics models in terms of precise predictions of where things will be. I think our models are much more about what happens when I apply this primitive skill to the world. Conceptually, what will the result be in terms of the relative poses of objects after applying this skill? So, you know, if I pick up a I don't know, it's a carton of milk and pour it into a cup, the milk will go out of the carton. But I don't know exactly how much, and I'm not reasoning about it in terms of volumes and velocities. I just know that when I do this thing, this other thing will emerge, and they're kind of concepts rather than physical states of the world. And we have models at that level that we are able to apply very, very broadly. And I think that's the level probably where the inductive biases should come in. We should be saying, you know, for example, you could say, well, let's learn 1,000 different primitive skills, and then let's learn and let's learn a representation of states that is at a more higher sort of symbolic level. And let's learn to combine those skills with those symbolic states to be able to then build a model. That framework itself is the inductive bias rather than the actual low level modeling of dynamics. So I think we can, you know, that's probably the level that I see for, I don't know, kind of medium term robot learning, beyond just sort of engineering everything, but probably before we actually reach AGI.
Makes a lot of sense. Okay, so I'll move on to the next question then. So again, relatively open-ended again, but the question just being, how much should we look to biology for inspiration? And to give some examples, you could say, are we in danger of solving needlessly complex problems if we don't, for example, explore soft robotics enough? For example, if you have a parallel gripper, the precision that you need to pick up certain objects, you know, might be much more than actually we do as humans, where actually we can just get our hand in the vicinity of the object, and we've got, you know, very, very sensitive hands with lots of nerves, very densely packed. You know, we've got soft, our hands are soft. So, you know, by the time we get to an object, we can kind of just, you know, feel our way around and grab it. And we don't need anything like as much precise visuomotor control to pick up an object, for example. So yeah, just generally kind of how much should we look to kind of the engineering side and the actual mechanics of the arm to maybe make the control systems simpler, for example? How important do you think that is?
So I guess biological inspiration comes at two levels. So you've got the biological inspiration from the brain, and then biological inspiration from the body. So at the brain level, I think that's, you know, it's really, really difficult. We don't really know what's going on in the brain. It may be that if we wait until we've understood that through neuroscience, then by that point, you know, we've already got AGI through another level. So I don't necessarily think that's the right way to be doing things. And then it's very tempting to look at the body and say, well, actually, that's something we can we can model much more closely. We can just dissect, bodies and look at what's going on inside with the muscles and the tissues. But I think the problem with that is, of course, the bodies and the brains have evolved together in a sort of joint optimization. And the reason why a particular body has evolved is because the brain itself has evolved in order to be able to control that body. And so if we simply say, well, let's take a particular body and build a robot equivalent of that, and then try and do learning with that body, there's no guarantee that actually the learning will be able to control that body. And so let's talk about the sort of a soft gripper idea. Well, it's true that if you have a soft gripper, that does facilitate picking up objects. And objects the grip can conform to objects. You don't have to be as precise, and the sort of softness of the gripper will allow you to have errors in control that you might not have if you had a rigid gripper. But once you pick that object up, then the fact that it's soft means that the ability to do something with that object is actually more complex than would have been if you had a rigid parallel jaw gripper. So, for example, if you were to pick up a light bulb and try and screw it in a socket, because you don't really know how to actuate that light bulb directly, the dynamics are very, very complex. And, you've got this soft tissue around the light bulb there's not really a very strong relationship between the pose of the light bulb and the actuation of the gripper. It then actually makes it even harder to do something with the object than it would have been if the gripper was rigid. And so that's where, I guess, with evolution, we've evolved to be able to control objects using soft grippers, or our hands. And when we would have to then do the same thing for robotics, but it does make the controller harder to learn once you've got an object in the hand. And I think grasping is such a big part of manipulation that people often overlook. Well, what on earth do you do with the object once you've picked it up? It's not, you shouldn't be optimizing everything just for picking up objects, because that's probably the easy part of manipulation. If you think of every manipulation task as, well, a lot of tasks is picking up an object and then doing something with that object. The picking up the object is quite easy, because we as engineers can define that. We can say, well, you just have to pick up an object such that it's stable within the hand. That's pretty easy to define, like a reward function for, or even engineer a solution for. The hard bit is then what do you do with that object once it's picked up? And that's the thing that we should probably be optimizing for, because that's the bit that we that is really, really difficult, and is extremely diverse and requires extremely high precision. So if we optimize too much for one half of pick and place, then actually that might make it harder for the other half of the pick and place.
Well, that's actually just an interesting point then, actually, just also that, so from my understanding and thinking about this, if you had a parallel gripper and you want to do something with the object, probably you're going to need to pick it up in the arrangement that you're going to act with it, pretty much. Whereas with a hand, for example, even though it's got substantially more degrees of freedom and you can't control it in the same simple way, you can just do inverse kinematics or something, and you've kind of solved the whole motion of the arm, and then you just put the gripper where you need it and you close the gripper. So that's kind of simple. And whereas with the hand, you've got, all these joints in it, it's very complicated. But actually, in terms of like what you can do with that, if you do write a good controller for it, what we can do, for example, is pick an object up and then quite easily rearrange it in our hands to then do what we want with it. So in a way, it's harder on the control side, but actually it is a lot more powerful in terms of what you can then achieve if you get the control right. So, depends then, I guess, where you see the biggest difficulty there. And maybe actually some people might then argue we should be focusing on hands and stuff because of where they can take us. And there's problems that we're trying to solve now in gripping, maybe in manipulation, maybe picking it up with the intent to move, that actually you don't need to solve if we get the hands right, because you can just arrange as you're moving. And then the other thing I would just say is that, like, obviously then we know in the human brain and also in control in general, things are very hierarchical. So with controlling a hand, we know that in biology, even I think there was a pretty grotesque example where they I think severed the head off a cat and we're able to stimulate the spine and essentially get perfect walking, and kind of actually all of the control for this slow-paced walking is all kind of in the nervous system, and it's not really even just in the brain. I'm not saying that's the same for us, but just there's very clearly this kind of, your brain sets the high level goals, and then there's this hierarchy of motion where actually closing your hand and doing this kind of, don't need to be handled by some master controller, but actually just by a low level finger specific controller or something. So anyway, so I've been monologuing a bit myself there, but do you then think that there is still a danger then with that example that we still could possibly solve problems that we don't need to, that might not need solving if we did master hands, for example? Do you think there's possibly a danger there?
Well, I definitely don't think there's a danger, because we always have to sort of move in sort of baby steps. So I think actually there's a bigger danger in saying let's only aim for the final robot that we're going to design, because it might be that that takes 100 years. Mm-hmm. And who knows, in 100 years time people might say, oh well, actually 5 fingers is not optimal, or some other kind of design. And then you could say, well, we've spent 100 years designing things around humans and now we realize that's not optimal. What a waste of time. So I think optimizing a robot around the human body is not guaranteed to be the optimal way for us to be doing research. So I think that designing robots with parallel jaw grip is perfectly fine for the first sort of generations of, let's say, domestic robots, or robots that can generally perform lots of manipulation tasks. And I think if you got there's a nice video I think from Princeton probably 10-15 years ago or so, where there's a PR2 robot roaming around that's controlled remotely by a human, performing lots and lots of tasks. So stacking a dishwasher, tidying up a living room. And it's a human controlling the robot, but the robot's just got a parallel jaw gripper, and that's a very old robot from, it's a good robot, but it's an old robot relative to today's robots. And that kind of shows that actually we can do an awful lot just with a parallel jaw gripper and very good control. So just because you can do more with a dexterous hand, it doesn't mean that we should be optimizing for that, because that might mean that robots take 50 years to emerge commercially rather than 10 years. And I think if somebody said to me, okay, you can either wait 10 years for a robot that can only do 50% of your domestic chores, for example, or you have to wait 50 years for the robot that can do 100%, I would say, well, let's wait. Let's get the 10-year one, and do things in the short term rather than only optimizing for the long term. Because by the time you've optimized for the long term, there's another long term that you might think, well, we should now be optimizing for that, and then you never actually converge on anything with any impact.
Yeah, that makes a lot of sense. So that actually then follows on very nicely to the next question. So this example you gave of this robot video from Princeton, which I'm aware of as well. So then I'm curious, what do you see as being the bigger challenge then, kind of solving general dexterity or actually understanding the desires of humans? And so what I mean by that is, for example, do you think it's more complex to translate any household task, such as clean and tidy the bathroom, into its useful subtasks, which might then be pick up the towel, put the towel on the rack, find the mop the floor, etc., or actually the completion of any one of these subtasks? Kind of what do you think, the decomposition of tasks into meaningful tasks, or actually subtask completion? Which of those do you think is more challenging?
I think the completion of the subtask is more challenging. I think it's a continuous control problem rather than a discrete problem in a sense. So I think that makes it harder. It's probably got to cover a higher diversity of states. So there might be a very large number of words in the English language, but there's an incredibly great number of different images of the world that you could possibly see. And also I think that a lot of this kind of this idea of decomposing a high level command like tidy my kitchen down to the primitive actions, a lot of that can be learned through sort of large language models and a lot of the work that's going on in NLP today.
One thing I'll just quickly say to that, sorry, is just that actually, I guess I would imagine a case where, for example, it is very much vision dependent as well. So when you tell your robot, clean my bathroom, it might be that actually the towel isn't always on the floor. It might be that, things are always in a slightly different state. So it also needs to query its sensors to kind of actually do that decomposition. It's not just about kind of, translating language or something like this.
Yeah. Yeah. So I suppose I guess you're asking, is it easier for a robot to decide what to do?
Yeah.
Let's say a robot had a set of 100 skills it could do, picking up a towel, putting it on a rail. Those are 2 skills.
Sure.
Is it easier to figure out which of those skills it needs to do at any one time, or is it easier to execute one of those skills?
Yeah.
I still feel like the execution of the skill is the harder bit. I think we're going to get, again, it's a bit more of a sort of discrete optimization problem, deciding which skill to execute rather than a continuous one. And I think the data that we will get for that is going to be, we're going to be able to generalize. It's just like, I think, for example, looking at a room and deciding what needs to be moved where, that just requires a single image, I guess.
I would say not necessarily, but I obviously see that, but I guess you might still need to get a 3D model or something possibly and kind of query on certain measurements still. But
I think that's then the control part, right? If you're reasoning about where does the robot need to move its hand relative to the object, I think that becomes the, how do I execute this skill of, picking up an object?
Yeah, well, I guess the two intersect a bit. I guess, I see what you're saying with it's just a single image, but I would just say it's maybe a bit more than that, because, for example, to see that the towel's on the floor in a room, you won't have to just walk in the room and take a photo. It might be you need to go around the table and see it. So all I mean is it's kind of not necessarily as simple as a single image, but still, obviously, it might just be a single observation of the room, for example. Maybe you first scan the room before, and then you decide. But yeah,
it's hard. It's a hard question to answer because actually we don't really know what this hierarchy is. It could be that it's very likely that we would end up with multiple levels of hierarchy where maybe the high level command is tidy the house, and then that's split into, well, okay, I've got to tidy each room, and then you go into the bathroom and then you see a towel on the floor, and then you think, okay, I've got to now put the towel on the rack, and then that requires grasping the towel, and then the grasping the towel requires then executing that. So there's lots of different levels, and it's difficult to know which ones are continuous control and which ones are discrete control. Difficult to sort of know what the intersection is between each level of the hierarchy, what information flows. Is it just a discrete switch as to which one, or is there also some kind of continuous variable which is passed across the hierarchy, the levels of the hierarchy, to then condition the next level of the hierarchy on the reasoning going on in the previous level? So it's difficult to sort of know what these levels of the hierarchy will actually be. But I think if we were to, if it was just a 2-level hierarchy and the question is deciding what to do at a task level compared to what to do on a low-level motor level, then I think the low-level motor level is much more challenging.
Sure. Yeah, that makes sense. But I also agree that it's not so easy to create these boundaries, and in fact, it is just a continuum of hierarchical actions to some extent, and that both are challenging, because even deciding what to do requires reasoning about uncertain observations and scheduling, and also probably redeciding in the process of completing tasks, and so on. So yeah, there definitely needs to be some kind of synergy between that lower and higher level components.
Yeah.
Okay, so I'll ask. So I just got a couple more questions. So again, this is actually very open-ended. So just how long do you think until we have affordable household robots that can, for example, reliably do our cleaning and tidying? What do you kind of think is a rough time frame on that?
Well, I think, it sort of depends on how skillful you want this robot to be. But if you're talking about, let's say, I mean, let's say a robot that would be able to do the job as well as a professional human cleaner, then I think, that maybe, I mean, it's so hard to predict these things, but I'd say certainly could be close to 50 years or so to really, or even longer, to really be able to do everything that a human can do. Even that sounds ambitious, because it means that possibly in my lifetime we would have robots that are as good as humans, and I don't really believe that. I guess with a domestic cleaning robot, you can engineer it to be optimal for a particular range of tasks, which makes things a little bit easier, and it doesn't necessarily need to have AGI. But I would say it's a long way away. But there's lots of intermediate robots between now and then, which will come in and will be able to perform tasks in the home in a way that is extremely useful and very, very desirable for society.
Yeah, that's a good thing with doing YouTube interviews. You can quote what the timeline you think, and in 10 years time or 20 years time, people can be like, oh, this is what Edward Johns thought. And it's like, it's so hard to predict these things, obviously.
Well, I should probably cover all bases then and just say everything, and I can cut the clip that actually ended up being true.
We can re-record.
I think it'll be in 5 years.
Times.
I think it'll be in 10 years. I think it'll be 20 years.
There we go. We'll cut it right. Don't worry.
Okay.
So that's actually very interesting. Then just so you were saying about these intermediate robots that are going to arrive between now and then, this hypothetical robot that really can clean and tidy at the same level as a professional cleaner. What do you think these intermediate, and maybe focusing on the house, because of course there's a lot of robots in factories and automation and that can do more constrained jobs. But do you think there's going to be a succession of household robots? Obviously, we already have vacuum cleaners. Do you think that's something that's going to kind of incrementally get more advanced over the coming decades, or do you think that's something that's more likely to only really hit the homes when it can really get close to that level of cleaning and tidying?
Are you saying will domestic robots emerge?
Will they emerge incrementally,
even though they're not as good as humans at different stages of commercialization?
Yeah, basically, yeah. Or do you think it's really just going to be no one buys them until they are close to humans?
No, I think there will definitely be a market for sort of intermediate level domestic robots where the robot may not be as good as the human, but still can perform a lot of tasks that we don't really want to do ourselves. If somebody said to me, there's a robot that can perform 50% of my domestic chores, and then I only have to perform the other 50%, that's great. And we do that already with various appliances. A washing machine doesn't fold your clothes, for example, so it only does half of the work. It does the kind of the washing part, but it doesn't do the folding or the ironing or any of those parts. And we're perfectly happy with that. We didn't complain that it didn't do the whole thing. Dishwashers don't stack themselves, and they don't unload themselves either. So I think we could easily see there being markets for domestic robots that do something in between a robot vacuum cleaner and a human that's still very, very useful and helpful, and people will pay money for.
Yeah, that makes a lot of sense. And I guess with some of these things, the good thing is with robots, even if it's not close to human level, if you do design it correctly, or maybe make it slightly humanoid or something, I'm not sure, there is then scope to have one that can do multiple of these tasks, which means you don't have to have a separate appliance that does your dishes and that does your washing or something. You can then possibly have one product that can actually fold the clothes and can, I don't know, do the ironing or do the dishes or something, and that's got a lot of strength as well over the current appliances we have, which are incredibly domain specific. Yeah, that's actually, I didn't plan to ask this, but just as a quick one then, do you think that that is the avenue that is more likely to be gone down, or do you think that there is actually a likelihood that we do get very domain specific robots?
Well, I think if you were to say, well, let's design a robot to do the ironing, let's design one to stack the dishwasher, let's design one to do the vacuuming, and have all these different robots, it would certainly make the design and engineering side easier. Commercially, that will ever really take off. You know, for one, where on earth do you store this sort of team of 10 robots? You know, there's not, you know, you don't want to be just clogging up your home with all these different robots.
Sure.
So I think this would only really work if there was like a single robot that could do everything for domestic robots at least, and then maybe there would be other robots for other areas of industry. But I think we really want that one robot to be able to perform a range of different tasks, rather than having to, you know, communicate to a different robot to sort of then roll in and take over. But it might be that, you know, robots would have different kind of tools that it could, you know, they can pick up and use, rather than having to do everything just with a gripper. So there are kind of ways around this, and maybe robots can be integrated with appliances. You know, maybe you could have a robot that's co-designed with a particular dishwasher, let's say. You know, and I can imagine you would, you know, the dishwashers and washing machines and fridges are all designed for humans, but there may be ways to adapt those such that it's a little bit easier for robots to interact with them. Rather than just expecting a robot to come in and deal with a environment that's designed only for humans.
Another interesting thing you said there is just that actually you don't want to clutter your house with like 10 robots, which is obviously very much the case. But you could then also like explore like more communal robots or rentals, or something that's more akin to a cleaner coming over, where maybe a block of flats has a few ironing robots and you book a slot, or, you know, they come to your door and stuff. So I guess there's lots of options to how this could unfold, but all a little bit in the future.
Yeah, it's an interesting idea. You know, if you share these robots across a group of people, that tends to not have worked, I guess, historically with consumer products. Like we don't do that with other things. We don't share our, I know, toasters with our neighbors. I guess toasters are cheap, so, you know, we don't really need to share them. We don't, you know, maybe the one equivalent here is, you know, some apartment blocks might have like a laundry room at the bottom where everybody would share the washing machines. But that's a little bit different because, you know, those washing machines, people aren't, those washing machines aren't sort of going in and out of different rooms. But yeah, I guess that's one option, you know, sharing these robots across people in a building such that they're not simply put in a cupboard and sort of not used for a whole week or so.
I guess the difference there, for example, with toasters or dishwashers or anything, is that actually if you get it right, that actually it could be much more convenient to share, because they can essentially, you know, knock on your door or something. It's kind of, you know, you could say that we I mean, I wouldn't use those words, but I mean, cleaners are, cleaners clean at lots of different houses and things, these kind of things. So there's situations where, of course, it's not like, I mean, yeah. So I guess there's the scope for people being interested in that mode, I think, of getting it. Okay, so sorry,
Yeah, I mean,
oh, sorry.
Yeah, just to add on, like, yeah, with cleaners, you don't hire a cleaner and then say you're not allowed to do cleaning for anybody else, and you have to wait
of course.
until it's you come back to your own place. So economically, that's worked quite well in that scenario. So yeah, this sort of shared robots idea it seems to possibly make sense economically. But I guess, like, the more complex and capable the robots become, the more likely we will want to use them for many things throughout the day.
Yeah.
So rather than just saying, well, let's do one cleaning up a week, it might be that multiple times a day we want to use a robot to, like, make dinner, do the laundry, clean up, all these things. And in that scenario, it may be that you just need your own robot that's permanently with you in your home.
Definitely, I agree. I think that's kind of definitely the end goal. That people would be most interested in and wanting everything with home robotics. But as you say, I guess kind of on the journey there, where the economic feasibility for consumers, as well as the engineering simplicity to make things as simple as possible for the people making them and everything, like, there's all sorts of kind of intermediates we could see along the way, I suppose. So we're getting close to the end of time, so I'll just ask the final question then. It's touching on what we've been talking about just there. So I would say, for example, robot vacuum cleaners haven't been a total revolution in the house, and the same is the case for robot gardeners, although they are seeing a lot of success and a lot of use. Certainly kind of most people don't have them. What do you think is the most important thing to really get right before robots can really revolutionize indoor cleaning and tidying? And what kind of is the thing that you think people might not be focusing on enough that they maybe should be focusing on a little bit more?
Yeah, so I guess, like, why do people not all have robot vacuum cleaners? Well, I suppose the reason is that you still need to vacuum, like, some parts of your house. So you still need to probably get a vacuum cleaner and go into the corners, for example.
And the stairs as well, I would imagine.
Yeah, stairs as well. So it's not like it completely replaces the need to vacuum. And then I suppose a lot of people think, well, if the robot doesn't do the job fully, then I still have to do it anyway. And the effort of going into the cupboard, bringing out a vacuum cleaner, and just going around the corners is almost the same effort as just vacuuming the floor in between the corners. But I suppose, it's like you yourself would do the spring cleaning, and then the robot vacuum cleaner would do the sort of daily cleaning, and that's maybe how it works. And you don't really need to clean the corners every day. It's something you need to do once a month or so. So I think, I guess it's also the cost. Robot vacuum cleaners are not that cheap. They're more expensive than just a vacuum cleaner itself. So there's that cost issue as well. I suppose in terms of what we need for the next generation of robots, probably the ability to do manipulation is quite important. So a robot vacuum cleaner doesn't really interact with the world beyond sucking up dust from the floor. It's mainly a robot that can navigate around and try to cover all of the floor space, but there's a very limited amount of change that a robot vacuum cleaner can sort of make to a room. So the next thing you would need is a robot which can actually physically manipulate objects and tidy the room using manipulation skills. And that's really, really difficult. Navigation is not very difficult relative to manipulation. We know how to navigate robots given a map of a room, and we know how to build maps of rooms. And and autonomous driving is way ahead of robot manipulation, for example, and it's essentially already commercialized, whereas manipulation in sort of unstructured environments is still somewhere away.
Yeah.
So yeah, manipulation is that kind of key technology, but it's not necessarily the case that people aren't working hard enough on it. I suppose if you really wanted to optimize the world around getting this first domestic robot with manipulation capabilities, then actually I would say we're probably optimizing too much on AGI and sort of long-term goals, and not optimizing enough on real world impact in the next 10 years or so. And so I think that would be one of the changes I would make if I were to optimize the world around designing research to bring about the first domestic robot. But as we spoke about, we need to have both long-term and short-term goals in research.
Yeah, that's very interesting. And I guess just as a final thing then, just kind of, do you think there is any possible danger, and well, not danger, but just for example, it is interesting what you said there. I would imagine that perhaps in the 1980s, people that were working very hard on getting real-world robotics for the home, it was a very long way off then, but there were people, I guess, that were very hard at work on a lot of key important work for motion planning and all kinds of areas of classical robotics. Maybe wouldn't have thought that, Geoffrey Hinton working on neural networks or something is really kind of on a path that is intersecting with robots in any kind of really relevant way in the short term, or at all, really, maybe. So do you think that there's a possibility that actually, because robotic is so hard, or something, that actually it could be that the people that are working on these longer term goals, end-to-end, actually it does so happen that in 30 or 40 years, actually it does have a much bigger role to play in getting the robots in the home than it might appear at the moment? Do you think that's a possibility, or do you think that's like, not that likely?
So unfortunately, my network cut out for quite a bit of that. Do you mind summarizing the question?
Sure. So I just said, just for example, in the 1980s, when, for example, Geoffrey Hinton and others were working on neural networks and backpropagation and all kinds of things, I would imagine that the people that were working on more classical robotic motion planning and lots of areas of classical robotics maybe would not have thought that actually this research on neural networks was likely to intersect on the route to getting robots in the home. Do you think that then it's possible now, given that we don't really know how close we are to getting proper, capable in-house robots, do you think it is still possible that the people that are working on these more like long-term general learning solutions, do you think it's possible that this will actually still intersect on our route to household robotics in the next 50 years in quite a strong way? Or do you think that's not that likely?
I don't think that, this sort of end-to-end AGI reinforcement learning work is going to really appear in the first domestic robots. It seems unlikely that these sort of very pure approaches that are essentially trying to train an agent with like as minimal engineering as possible are going to intersect this sort of route to commercialization for the first domestic robots, because I think there's a lot that we can do without end-to-end learning, just by modeling and using machine learning, certainly, but only for the parts that we don't know how to model. And I think that robot itself, once we've done a really good job of the engineering side, can be very capable, and we've just got to spend time doing it. So I think the intersection between the more kind of long-term AGI machine learning research and say commercial robotics will be in much more in the future when we want robots to be able to do things that we actually cannot really engineer solutions for, or where any kind of engineering is a bias that we want to overcome. But I don't think that you need end-to-end reinforcement learning for a lot of the sorts of tasks that you would want a robot to do for the kind of first generation of domestic robots, because I think that there are simple things that a robot can do which are still very useful around the house, and I think to be able to get robots to be able to perform those simple things, we can engineer the system such that we know what needs to be learned and what doesn't need to be learned. And I think there might be roles for deep learning and reinforcement learning and imitation learning, but as part of a bigger system rather than as this sort of pure technology which is going to drive the entire robot's algorithm.
Sure, that makes sense. Okay, well, I think we're kind of approaching time now. I don't want to take too much time out of your day, so I think we'll kind of wrap it up there. But thank you so much for taking the time for this interview. It was a super interesting discussion.
You're welcome.
Yeah, and so we're going to have more roundtable events at conferences in future, and we'd love to have you join again some of these other events, and love to keep discussing with interviews as we keep going and keep these discussions going. Will be really great. But yeah, it was a real pleasure to sit down and talk with you. And yeah, thank you very much.
Yeah, thanks so much, Dan. Really, really interesting, and thanks for putting together the roundtable. It was really, really, really great, and I thought this discussion was really fascinating. Just to sort of, just put my own thoughts into my head, really.
Yeah.
Sort of.
Yeah.
To become aware of what my opinions and thoughts are. Sometimes you have to be asked questions to actually know what you believe in yourself.
Yeah.
And so I think that was really an interesting experience for me as well. So yeah, really, really interesting. Thanks very much.
Yeah, of course. No, I'm glad you enjoyed it. I'm exactly the same. Like, you don't really know what your thoughts are until you've had the chance to bounce them off someone. So yeah,
exactly. Yeah.
Okay, yeah, well, great. Well, thank you very much, and see you next time.